let's continue. Okay. So, well, this projection I already explained, right? So projection like okay, v1 to vi minus 1 is just if you try to project vi to this one, because the span of this one is the same of the span of this one, and this is orthogonal, right? So just like it's going to, you can represent this projection by this. And then, that is why, like in the process previously, like your vi minus this one is going to be orthogonal to any vector split by, this v1 to vi minus 1. So this is, like example, this example is a little bit more complicated, okay, because it's, P2, okay, the polynomial up to degree 2, okay. So that x1 equal to negative 1, x2 equal to 0, x3 equal to 1. By orthonormal basis for P2, if the inner product on P2 is defined by, be very careful, this inner product definition is different. This is different from the previous definition of the inner product for P3. If you remember the inner product definition for P3, this one. The definition is different, right? The definition is different. So you need to be very careful, okay? Okay. And this definition, okay, by the way, it has specifically like involving those x1, x2, and x3, by the way, in this definition. So it is not just like, so this inner product is not just like, you just look at the polynomial and you can decide what the results will be. You have to plug in those x1, x2, x3 there. Okay. So here we have a basis. v1 is 1, v2 is x, v3 is x squared. Okay. So first, for v1, okay, we want to construct like w1, w2, and w3, which are orthogonal, and then we need to construct u1, u2, u3 from w1, w2, w3, so that like u1, u2, u3 are not only orthogonal but also unit vectors. Okay. So first, for w1, we know w1 is u1. So w1 is v1, so it's just 1. And the norm of w1 is going to be the square root of like w1 inner product w1. So you need to plug this, put this here. So your w1 is just 1, right? So 1 times 1, okay? It has nothing to do with like the x value. So 1 times 1, I from 1 to 3. So that's 3, right? So it's square root of 3. So your u1 is going to be w1 divided by the norm of w1. So it's going to be this one. Okay. And then it's w2. W2 is the v2. It's going to be v2 minus, okay, V2 dot W, yeah, W1, okay, divided by, well, W1, and this is V1. Okay, this is the projection of V2 on the space that is spanned by W1, right? So then, okay, this is the W2. So this is V2 is X minus this is like when dot W1 is 3, right? Okay. And V1 is 1. And V2 dot W1. V2 dot W1. V2 is X. Okay, X is so P is X, and the Q is 1. Okay, so if you plug in X1, so it's -1 times 1. So the first one is -1, and the second term X2 is 0. So 0. So times anything is 0. The X3 is 1. 1 times 1 is 1. So -1 plus 1 is 0. So the whole thing is 1, is 0. Okay. So, well, oh, sorry, let me square it. Let me see. Yeah, it's this one. That's correct. So this is X. So that's like W2. But we need to calculate, like we need to, make it univector. So the U2 is going to be X divided by the norm of X, or like X. Okay. So it's going to be, probably this one, like the first one is 1, the second one is 0, the third one is 1. So it's square root of 2. So it's going to be square root of 2 X. So this is U2. So W3 is going to be V3 minus the projection of V3 to the space that is expanded by W1, W2. So it's like V3 W1 V1 sorry, W1. Okay, this should be W1. This conceptual is more, makes more sense. Plus V3 W2 Okay, so V3 is X squared. Okay, and then W1 dot W1, I think we previously calculated is, what's that? W1 dot W1. 6. W1 is where's W1 is W1 is here. The square root of W1 is 1. So it's 1, 1, 1. Okay. So it's 3. Denominator is 3. Denominator is 3. Okay. And then B3 is x squared. W1 is 1. So x squared, 1. So it's 1. Second one is 0. Third one is 1. Okay, so it's 2. So 2. Okay, times W1. W1, what is that? W1 is here is 1. Okay, so we have this one. Minus. Where is this? We have the first term from here. The second term. W2 dot W2 dot W2. W2 is x. Okay, so x dot x is let's see, is 2. No, it is 2. Okay, and then D3 is x squared. W2 is x. W2 is x. Okay, so x squared. So 1 dot times x is negative 1. So it's going to be, the first is negative 1. The second one is 0. The third one is 1. So cancel out each other. So this one is 0. Times W2. Okay, so the result is going to be, well, this one is gone. So it's x squared minus 2 over 3. Okay, x squared minus 2 over 3. And then your W3 is going to be, the node W3 is going to be this one, inner product, this one, and square. Square root. So it's going to be we plug in this this is x squared. Sorry, W3. So W3, so we need to do this, so plug in this one, x squared minus 2 over 3. If x1 is 1, negative 1, sorry, x is negative 1, so it's going to be 1 minus 1 over 3, so it's 2 over 3, it's going to be 1 over 3. So it's 1 over 3. Then the second one is 0 minus 0. 1, this one squared plus the third one is again. So it's going to be 9, 1, 4, 1, 6. So it's like 3, 2, and then get like square root. So this is like it's this one. This one. And then U3 is going to be this one divided by this. So it's this one. Okay. So you can see that. Okay. It has a lot of calculations. The reason is really because like the inner product here, the definition of inner product here involves like some additional like you know, xi's, and then like complicate like the whole computation. But the basic idea remains the same. Okay, nothing is new here, except like that we have a new definition of inner product. Okay, and the last one. Okay, the last one is that. Okay. So we have like the Gram-Schmidt autonormalization process. Okay, I previously told you there are 2 steps, right? So that's if we try to write it into, write it together, then W1 is V1, and then U1 is W1 divided by its norm. And the W2 is V2 divided minus this one. Okay. Be very careful. We use U here instead of using W1. We use U here. So that's why we don't need to divide it by like the W1 inner product W1 here. So because it's a unit vector now. Okay. So this one, and then once we get W2, okay, U2. U2 is going to be W2 divided by, this is a typo, this is U2. So U2 is W2 divided by the norm W2. And the W3 is V3, okay, minus the projection of V3 onto the space that is spanned by U1, U2. So it's, it can be written like this. And the U3 is going to be W3 divided by its norm. Okay, and so on. So it's a little bit cleaner because we are in here we directly use UI here. So the B prime is an autonormal basis for B, and this B prime is consisting of like a U1, U2, and so on. Okay, basically we already know that. It's just like we try to combine these two. Why do we need to do this? Why do we need to do this? Because there's something very interesting here. Okay, it has something to do with like matrix decomposition. Okay, that we are going to talk about here. This decomposition is called Gram-Schmidt QR factorization. Okay. So if A is an n by n matrix of rank n, okay. By the way, okay, if you look closer, you will see that n must be greater or equal to n. Okay, but once if you understand that this, remember, if you still remember what we discussed for the rank, this goes without saying, okay, if this is n by n matrix of rank n, then n must be critical equal to n. Otherwise, like, if n is more than n, the rank cannot be n. Okay, you will know that. Then A can be factored into a product QR, where Q is an n by n matrix with orthonormal column vectors, and R is an upper triangle n by n matrix. So it's an upper triangle n by n matrix whose diagonal entries are all positive. It's a kind of interesting. Actually, the idea here is just we try to write the whole thing, the whole Green's mean, like autonomization process in a matrix format, and you will derive these. I mean, it's not obvious, I understand, but it is like actually easier than you may think. Okay. First, okay. This is n times n, right? We have n. Actually, should be a little bit longer. We have n rows and columns. So you consider this column vectors. They are n column vectors, right? They are n column vectors, right? So if you try to remember here we said this is rank n, right? Right? So if you still remember the rank discussion we had earlier, then you will understand that, okay, this n column vectors, the space generated by these n column vectors is of dimension n, right? Is of dimension n. If you still remember the previous discussion on rank, okay? And then, okay, what does that mean? That means these n column vectors are independent, or you can say like, okay, they can form the basis for the column space, right? They can form the basis for the column space. Okay. Then obviously you can apply Green-Smith orthonormalization process on these n column vectors, right? Right? Good. Then what happens? Okay. Let me try to write it. Okay. Now, I want you to remember. Okay. Our V1, V2, Vn are the column vectors here. Our V1, V2, V3, okay, are the column vectors. So this is V1. This is V2. This is Vn. Okay? And then, okay, think about this. And if you are going to write, okay, so let's say like eventually you finish the Green Smith auto normalization process, and those like n u1, u2, u3 to un. I mean, you can write them here. This is u1 to un. So okay, this is n by n. This also n. This is also n by n, by the way. Right? Right? Any question about that? Because we are these two set of vectors generating the same Collin space, right? Okay, they are generating the same Collin space, right? So, what I want you to think is the relationship between this and this. Okay, let me write it. Okay, this is the original formula, but let me write it in reverse order. Okay, I mean let me try to represent ui by wi by vi. I'm sorry, represent ui by vi. Here we are trying to derive ui from vi, right? This formula allows us to derive ui from vi, right? Any question? No question, right? But now, I mean, if you can derive ui from vi, obviously we can derive vi from ui as well, right? From this formulas, right? So the first formula, obviously, V1 is what? Is well, we know like W1 times the known W1 times U1, yeah, V1 equal to, okay, V1 basically equal to W1 equal to, and then we have U1 equal to W1 divided by its norm, right? So then, what is the, if you want to represent V1 by U1, then basically V1 is W1 U1, right? Right? Any question? Right? So far so good, right? Then how about V2? Okay, V2 is W2 plus this thing, right? Plus this thing. Okay. V2 is W2 plus this thing. process U2, U1. V2, U1, V2, U1. U1. Okay. And then remember, we also need to multiply because we want to represent the we want to represent like this thing by U, okay, let me see. B2, okay. Anyway, what I want you to understand is that this UI times the first one is all the other is 0. Okay. If you look at here, okay, this is n by n. Okay. The result of the first, result of the first line will be this line times W1, right? For the V1, right? If you write this one equal to this, right? Right？ 就是你看，这一行是不是就这个东西乘上这一行，就是会得到这个第一个 column， 或者说你可以讲过这一行就是把这些 column 做一个线性组合得到这个，对不对？那我刚刚也跟你讲说，你用 U1 来表示 V1 的话，其实你的 V1 就是这个 W1 的 norm 乘上 U1， 所以你这个第一个是 W1 的 norm， 其他都是零，对不对？对不对？了我的意思吗？你只是把刚刚的 Grant Smith 那个 process 把它写成矩阵的形式，只是你写反过来。OK， 那第二项呢，你会有2项，因为你这个，你把那个 U1 U2 做一个线性组合，你就会组合回来 V2。OK， 那第3项，你这个 V3，你用 U1 U2 U3 做线性组合，你就会组出来 V3 ，and so on。Okay, so this is like a upper triangle plot, like this matrix, this n by n matrix, upper triangle. Okay. Something like this. Okay, and also. I mean, you can easily, I mean, you need to try to write it careful. You will see that, you know, this Rij, okay, this Rij is like you know, is it's in the product, okay. And I believe I guess it's R11 Q1 and the blah 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 R1 K blah blah. So this actually represent like the Green Smith decomposition, this decomposition actually just means you try to write of normalization process and reverse it. Okay, and this Q1, Q2, blah blah blah. It's just this is our, what should I say, UI, and this R, IJ, okay, and remember this yeah, diagonal entries are all positive. And what are these diagonal matrices? Diagonal element in this matrix. This diagonal just means why are they all positive? Because in this process, we always need to when we obtain a UI, we always need to divide it by a node, right? Divide I by its node. And that node, I mean, when you write it back, this thing has to be multiplied by W1, W2, the node W1, W2, and so on. So those Wi, the node Wi, will appear in the diagonal elements. Okay, so that is why. Okay, that is why these diagonal elements are all positive. I mean, the easiest example you can see is W1. Okay, the second one, it takes some effort to basically represent your U2 by U1, B1, B2. And you will see that, the second term is also the node of W2. Okay, and so on. So you will, let's just look at this example. Okay, I'm sorry, I spent too much time on this. So this is we want to do this Green Smith QR vectorization. So basically, okay, you will find that, okay, this, we want to do this 1, 2, 2, 4, negative 2, 0, negative 4, 0, and negative 1, 1, 2, 0. So we have these three vectors. So, basically, what you are doing is basically you are just trying to decompose this, applying the Green Smith process on these three vectors. So the first one you get is this one. Why? Because this is your U, this is B1, B2, B3. This is U1. This is U1. You will see that obviously this is 1, 2, 2, 4, right? 1, 2, 2, 4. So you just divide this by 5. Because once you do that, it's the denominator is 35 and the numerator is 1 plus 4 plus 4 plus 16. Yeah, so it's 25, right? So this is univector. This is you make the first vector univector, so this is what you have. And the second one is you subtract the projection, okay, of this one on this one, and then you do you try to divide the node. This is the third one. The third one, again, you subtract the projection of this vector to the space spanned by this tube, and then you divide the node. You Okay, this one. So these three are U1, U2, U3. And then, this numbers actually has something to do with the Gram-Schmidt like autonomalization process. First, like 5, 4, 2, that actually represent like the length of W1, W2, and W3. And this, sorry, I'm running out of time, but I will go over the whole process of this next time. Okay, but basically, like it's just like this decomposition just means that you try to write the Gram-Schmidt like autonomalization process like into matrix form. Okay, so you become like factorization of the matrix. Okay. Okay, that's probably about it. So the next quiz, okay, will cover this chapter. Okay, even though like we don't have enough time to finish this example, but I think like I will spend a little bit of time like to talk about this example, at least go over the whole thing, like at the beginning of next lecture, and then next week I'm going to the third class I'm going to give you a quiz, okay, that cover whatever whatever we finish like for quiz 4, okay, to the end of this chapter, and then just want to remind you that I'm going to upload the practice question later today. Okay, any question? 问一下，我那个期末考的那个练习题有放上去了吗？还没有对。Okay, I'll ask the PA to do it. Okay. Okay, I'll upload the final exam, sample final exam.